So I'm going to talk about, is science slowing down? And then I'll kind of set the scene and then hand over to Maya, who will talk about medicine more directly. So there is a lot of stuff in the media claiming it is. So if you are reading the New York Times, the Atlantic, in fact, the Economist, the Wall Street Journal, Vox, there's a pretty regular drum roll of media articles claiming science, progress, innovation, pretty much whatever you call it, is slowing down and getting harder and harder. And there's some serious research underlying this, which I'll kind of talk about in a minute. But there's also some anecdotes that maybe people also kind of concur with. One of them is, look at all the iPhones. So, when you went from iPhone 1 to 2, that was a huge improvement, but each extra new iPhone that's coming out doesn't really seem much better than the one before. Or laptops. I remember, I got my first laptop in the mid-90s, and they were getting better rapidly. Now, they seem the same. One of the journalists talking about movies, saying, have you noticed all the movies in our sequels, like Iron Man 3 or Toy Story 5? And, it's like, why is Hollywood not coming up with any new ideas? As I mentioned, there's some serious research behind this. Here is a paper in Nature that came out last year. What this paper does is it looks at two different main databases. So tens of millions of patents, basically every patent in the US going back about 100 years, and several million journal articles from Web of Science. And what they do is talk about the CD index, which they call the consolidation or disruption index, and how this changes over time. So the way they do it is take a paper. They say, when a paper comes out, they're going to think of it as consolidating if after it comes out, people not only cite that paper, but continue to cite the papers that paper itself cited. So it's kind of consolidating what's come before. They claim the paper is disruptive if, on the other hand, a new paper comes out, and from that point onwards, everything cites that paper and kind of forgets the literature before it. It's kind of changed the paradigm shift. And you can argue about how perfect this measure is, and the paper does a lot of that. It basically shows, and this is the figure on the right, that over time, publications and patents have become more consolidating and less disruptive. And they claim that's kind of a measure of science is less innovative, it's more it's less kind of breakthrough over time. Interestingly, and this will come back to what Maya's going to talk about later, if you look at life sciences and biomedicine, that has one of the that looks in some senses the healthiest. The decline of innovation is the least, and in fact over the last 15 years, 20 years, from the mid-90s, it looks like it's flat. So in general, it claims science is declining and becoming less innovative over time. It's less obvious that that's true for medicine for the last 20 years. There's also tech titans who've made similar claims. So Peter Thiel claims that science is stagnating. Given many of the claims Peter Thiel makes, I believe the exact opposite. I don't know if this is helpful or not, but Peter Thiel, he certainly believes that science is stagnating. Perhaps, I take this in a sense more seriously. Patrick Collison, the founder of Stripe, who's fantastic. I think his wife is actually in the university. Michael Nielsen, who's a science journalist, had a study whereby they persuaded about 100 academics in physics, separately in chemistry and separately in medicine, to say when they thought the biggest Nobel Prize winning breakthroughs happened, which decades. And what you can see below is in physics, it looks like, it's kind of flattish, but physicists claim maybe the 20s were the most exciting for breakthroughs that ended up in the Nobel. For chemistry in the middle, it's basically flat. For medicine on the right, again, it's hard to know, but it's possibly higher in the 50s and 70s. But, if you look across all of these, they're basically pretty flattish. The critical point is top right, the graph, which shows inputs into science. You can show an explosive growth rate. So how many PhDs, how many publications, NIH, NSF funding, all of this has gone up by about 100-fold since the mid-1950s. And so the argument here is, look, output is kind of constant, but inputs have gone up by about 100-fold. So it suggests it's getting harder and harder to make breakthroughs. Maybe, but one argument you often hear is, look, one field slows down and another is born. So at the field level, maybe physics is getting harder to make breakthroughs, but now people are putting energy into engineering, or maybe engineering slowing down and people are putting energy into computer science, etc. So the way to get around that is look at the entire of society, look at everything together, which kind of includes extensive and intensive margins. So one way to do that is, as an economist, you'd focus on what's called productivity growth for the whole economy. So this idea goes back to Robert Solow. Robert Solow, was an incredible character, died aged 99 just at the end of last year. He won the Nobel Prize. Perhaps as amazing, 5 of his students also won the Nobel Prize. 4 in economics, and in fact 1 in medicine. Robert Horvitz won was a Bob Solow student. Solow did a lot of work, but one of the main things was on measuring and thinking about productivity. The simplest measure is output, or value added, to be slightly more technical, per hour worked. What does that look like? What does productivity growth in particular, which is a kind of an economy-wide measure of progress, look like? Well, here's a figure. Goes back to about 1750, 1760. What can we see? First thing is, from the 50s, yes, productivity growth, so some kind of rough measure of the progress of society, of the economy overall, has been slowing down. So that's what people have been bemoaning and mentioning, and this is just a big picture panel on this. But to be somewhat more optimistic, it has before that been actually increasing for a couple of hundred years. And in fact, if you go back further, for this you have to use English data because it's hard to get, there wasn't really any data much in the US before about 1700. But if you look at, say, Madison has some data for England, looking at progress back to about 700 AD. So if you're watching those Viking TV series on, say, Netflix, you know that 700 AD is basically when they had the Saxon kingdoms of like Wessex and Northumbria. And they have some records going back, and they can figure out roughly people's food consumption, housing, clothing, etc. Turns out people got about 3 times richer between 700 and 1700 AD. So yes, that's good, but that's over 1,000 years. And if you compound that, that's less than 0.1% a year. It's actually about 0.05%. So productivity growth in society was pretty flat up to 1700. Then we have the Industrial Revolution. It's a big deal. Productivity growth starts to really pick up. The next critical thing is potentially Edison Labs as an example of commercial R&D labs. So Thomas Edison was the first person to set up a lab and sell the patents. He basically had, for-profit innovation. Then you start to have the big rise of commercial labs. So General Electric, here's a photo from GE Labs in 1900. It actually has Whitney and Marconi are 2 of the 3 people standing there. NSF in the 1950s. So there is amazing progress. And yes, maybe progress is slowing down over the last 70 years, but we're still at a pretty good point compared to longer run trends. It's also slowing down, recently across all rich countries. So it's not just a US thing. Here's 30 of the world's top, richest countries from the OECD. 29 of the 30 are seeing slowing productivity growth. The only one, I don't know if anyone's fast enough to look at these bars, is Spain. I don't know what's going on in Spain. I know they've done very well recently in football, winning, various men's and women's. They won the Women's World Cup, but I don't think that's part of the productivity story. But broadly, productivity growth is slowing down globally. So why is this? I'll go through 4 explanations and then hand over to Maya. So I'm just going to call these the Fantastic Four. These are the ones that often come up. So the first story is measurement. So maybe you just mismeasured it. And it's initially really seductive. This is a story you think, wait, this data is not very good. For example, think of the internet or social media. If you think that's positive, it's free. It's typically not patented or in publications. No one's measuring it. Think of connectivity. But the complicated thing is there are a lot of innovations, if you go back in time, that are also probably not very well measured. Think of, sanitation, law and order, the radio. These also generated amazing gains. Much of it was free. Maybe much of it was never patented, or some of it was never written up in journals. To make it more complicated, in order for mismeasurement to account for slowing productivity growth, it's not just that there has to be mismeasurement. It's not just that this has to be growing over time. It has to be growing at an accelerating rate. So this is really a story about the second derivative. The studies looking at this find, if anything, it goes the reverse. So mismeasurement is one of those stories that sounds initially really seductive. It turns out the evidence goes completely against it. So I think it's no. Second story is maybe declining dynamism. It's harder to be dynamic, creative. There's a lot of regulations. You know, in relation to medical research, my father actually runs a lab. He's just kind of retiring in the UK. He's been running a lab now for more than 30 years. You know, it's been very successful. They've had startups spun out. You know, people in the lab have many papers in Nature and Science, etc. When I've talked to him about it, he certainly says that the regulatory environment's getting tougher. There's more form filling, more regulations, more permitting, etc. But the magnitude of this, the magnitude of aging, the magnitude of this kind of decline in dynamism is probably not big enough to explain the enormous slowdowns in science. So maybe, but I don't think this is the main story. A third explanation you hear is basically kind of bad luck. So folks will say, well, you know, the last 20 years has been really hard. We've had, you know, oil shocks, wars, COVID, the global financial crisis. It's just been a horrible 20 years. And that's, you know, been, you know, a continuous punch in the face for science and research. Maybe, but, you know, if you look at the peak period, the 50s, 40s, 60s, that was, you know, pretty traumatic with obviously World War II, you know, Vietnam, Korea, assassination of the president, you know, all kinds of things. So I don't really think this is a big factor. I think probably where the most mileage is, there's this thesis that people are running out of ideas. So what's this thesis? Well, there's a famous book by Robert Gordon that won various awards. I think it won the New York Times Book Award, etc. This book's pretty fascinating. It's you know, if you have trouble sleeping, maybe it's a good read before bedtime because it's about 600 pages full of facts. But Bob Gordon's big thesis is the major innovations in America, the things we all care about, all happened from 1870 to 1970. So he's claiming the really big deal things like, you know, electricity, air conditioning, refrigeration, indoor sanitation, all these things happened over those periods. And from the 1970s onwards, there's much less important inventions, you know, social media, maybe computers. Some senses they're a big deal. Bob Gordon's kind of party piece to persuade people that is, he says, look, when he gives talks, he polls the audience and says, look, which of you, you know, put your hand up if you'd prefer to have indoor sanitation, so baths, showers, toilets in the house versus, you know, a cabin in the backyard, or you prefer to have a cell phone. And of course, everyone would rather have, you know, a toilet, bath, shower in their house and having to go back into a shack in the backyard and give up the cell phone. And so he uses that to argue the basics of life, you know, were invented in earlier century, and in the last century, and innovation is slowing down. Tyler Cowen has a, you know, a similar version of some politics thrown in. So what's the evidence behind that? So I have a paper in the American Economic Review. It's our Society Journal with Chad Jones, who's actually at the business school, John Van Reenen, who's at MIT, and Mike Webb, who was at Stanford, who was a former student who amazingly has gone off to try and set up his own university. He's getting some traction, but it's pretty ambitious for a student. So what do we find in this paper? Well, we find that research productivity, very basically measured, does appear to be slowing down. How do we find that? Well, you know, here's one example graph. On the left scale is the growth rate productivity in the US economy, and that has roughly halved since the 30s or 40s. So productivity growth used to be 2-3%. You know, growth in general in America is very high in the 40s and 50s. It's slowed to 1-2%. It's not catastrophic, but productivity growth is clearly down. On the other axis is the number of researchers, how many, you know, scientists, or how much we're spending on R&D in real numbers. That's gone up a bit over 20-fold. So you can see now from this that, look, you know, innovation or growth rate per dollar or per scientist appears to be down, and it's down by a factor, you know, an extremely large factor, almost 50-fold. One example that's easy to think about is just Moore's law. So initially, Moore's law looks like it's evidence for steady progress, which in some ways it is. So Moore's law is the number of transistors on a microchip, and it roughly doubles every 2 years, and it's been incredibly stable, actually, going back from 70, you know, from Gordon Moore's kind of the era of his original predictions back in the 80s, back to 2020. So 50 years, just astoundingly stable. But over that time, the number of scientists and engineers, the R&D spending has gone up in real terms about 20-fold. So the argument is it's getting ever harder to make progress. So probably, you know, possibly running out of ideas. maybe. I mean, that's the evidence that you can, somewhat backward-looking evidence. Before I end, I'm going to point out there's two massive buts, two massive kind of concerns with this somewhat pessimistic view. First is past does not predict the future. So this is all backward-looking. It could be that AI radically changes everything. Maybe it's not, it's somewhat unlikely in the sense you've only really had two big turning points in history. There's, 1750 where suddenly productivity growth starts accelerating and 1950 where it starts slowing down. But it's certainly possible that, 2020, the 2020s, say, are another turning point. Secondly, I think more relevant for the audience here is this is all of the economy, all science, which is what the media is focusing on. But maybe medicine is different. And if you looked at that Nature paper, as I mentioned earlier, the prognosis for medicine is a lot more positive, particularly over the last 20, 30 years. So at this point, I'm going to hand over to my fantastic colleague, Maya, who's going to talk about her research on medicine.
Great. Let me share my screen. All right, I think that worked. Okay, I'm really excited to be sharing this with you all today, in no small part because a lot of my research as a graduate student has been inspired by many of Nick's papers, and so it's a lot of fun to be able to share this space and have this conversation with you all today. This project is part of a larger collaborative effort with Sipri, who is a PhD student in computer science, and David, who is a PhD student in economics here at Stanford, that at a high level is trying to construct high quality measures of innovation in medicine. This is a much more technical project than kind of the 10,000-foot view that Nick is giving you of what are trends in the economy. What I kind of find the most interesting in research is figuring out what exactly it is we're supposed to be measuring. So I want to start by contextualizing a little bit where this project came from and what policy discussions are useful to have in the back of your mind as we talk about what really is a very technical, what is research productivity in medicine? What's the input? What's the output? So a lot of my work right now centers on what I think of as something of a puzzle in biomedical markets. Around the year 2000, the popular consensus was that basic scientific research related to medicine was about to become much cheaper. And all of the types of headlines that Nick was showing you 25 years ago were about how the next big revolutions in diagnosis, the next big revolutions in therapy were on the horizon. And this was for good reason. The Human Genome Project had just been completed. There were enormous developments in DNA sequencing and combinatorial chemistry and the use of transgenic animal models and lots of other things about science that you all understand much better than I do. But with every one of these breakthroughs, the idea was costs should be falling. But if you open any economic report of the president since 2018, you read reports coming out of Brookings and the CBO, you open the op-eds in the Atlantic and the New York Times and Vox that Nick was showing you, the policy consensus appears to have extrapolated from this kind of economy-wide slowdown evidence to also say maybe medical research also is in a state of decline. That is, even though costs have gone down and opportunities for research should have gone up, the consensus appears to be that we are spending more and we are getting less. And I say this very skeptically because I think that the evidence on research productivity in medicine is very thin. And this is a setting where having really good evidence is really, really important for policy. We're already seeing the implications of this narrative of declining research productivity in medicine in Washington. In the past couple of years, there have been calls for more lax evidentiary standards at the FDA. So relaxing the costs of clinical trials because apparently costs are rising. Completely overhauling and restructuring the NIH, changing the way that we allocate grant funding to scientists, rejecting any proposal to cap drug prices within federal insurance plans, because if medicine is in a state of decline, if we're going to keep needing to spend more and more money, we need to figure out how to constrain costs in some way. Today, I'm going to make what I think of as a relatively strong claim. I'm going to argue that the best available evidence suggests that these patterns that Nick showed you for other fields of the economy, for other aspects of scientific research, are different in medicine. It looks like probably since around the year 2000, but my data are best from 2010, research productivity in this sector is essentially stable. So when economists talk about research productivity in this setting, you need some measure of inputs and you need some measure of outputs. And this is a very, very stylized object. So for every unit of research that we put into producing new ideas, we need to have some sense of how many new ideas are actually realized. So I'm going to make this concrete in medicine with a whole bunch of caveats, mostly to satisfy my physician scientist, basic scientist parents who objected to some of this. I'm going to say when we think about translational medical research productivity, we're thinking about things like how many dollars are we spending, how many publications are being written, how many clinical trials are being run, and how many inventions do we see in the economy that are actually impacting patient care. So there's this whole upstream world of understanding the basic science that goes into every drug that's developed. But what we really want to know is on this question of translational medicine, how much are we putting in and how much are we getting out? There's two stylized facts really that are driving the discussion about research productivity in medicine. The first is that the number of drugs that come to market more or less since about 1990, with a little spike for antiretroviral drugs in the early 90s, it's more or less constant year to year. Improvements in life expectancy, improvements in mortality, these are actually quite stable objects. And this is an important kind of separate question about whether these improvements in human health may also be stagnating. But it is a fairly robust fact that the numerator here is constant. And so I'm going to treat that as essentially we're getting the same amount of outputs year on year. And the big question is how much are we actually putting in? The number of dollars that the pharmaceutical industry says that it is spending on research and development each year, the total quantity of scientific publications in PubMed, and the quantity of measured clinical trials, all of these appear to be increasing sharply. And so these are kind of the facts that we've had to work with in this discussion so far. And so if the numerator is constant and the denominator is increasing, this implies that translational medical research productivity, must be decreasing. So if the numerator is getting really big, or the denominator is getting really big, the numerator is stable, research productivity is falling. That's kind of where this discussion is coming from. My work in this space is kind of trying to interrogate the way that we're measuring these two sets of objects. Because when you stop to think about it a little bit, and I suspect that you all are as skeptical about some of these things as I am, measures of pharmaceutical research spending, total number of publications, clinical trials, these are all kind of hard objects to pin down. And in particular, the best measures that we have of R&D expenditures in the pharmaceutical industry are self-reported by industry. So I had a really interesting conversation with a member of the Senate Help Committee who was thinking about reforms for drug pricing a couple of weeks ago. And I asked him what kind of was at the top of his list of things that he would like to know as a policymaker. And the number one thing was, what is the cost of R&D? Do we have disaggregated measures of how expensive it actually is to bring a drug to market? And I think as far as a lot of people are concerned, we have some kind of rough estimates, but it's a hard thing for us to take super seriously and draw big conclusions about kind of the structure of the economy and changes in these markets over time. It feels like a weak evidence base to be making policy on. The second fact, which is part of what comes out of the Nature paper that Nick was showing you, is that the number of publications in PubMed is increasing over time. I suspect it's not surprising that the total quantity of publications isn't a great denominator for how much research effort we're putting into something, in part just because all publications are not the same. Some publications are much better designed than others. Some involve many more scientists or many more grant dollars. Some are written because somebody is applying to graduate school and needed to have a publication. And so if you were to just weight every single paper in PubMed in the same way and observe, the number of publications is increasing over time, it doesn't tell you a lot about the question we're really interested in, which is it harder for us to get technologies out of inputs? I'm going to suggest to you that the best proxy that we have for translational medical research productivity comes potentially from counting clinical trials. And this isn't because there aren't other measures of how much research effort is going into medicine, but it's a snapshot of how well this ecosystem is doing at translating ideas, essentially from bench to bedside. The nice thing is that trials are discrete, regulated experiments that are in principle consistently disclosed in journals and in administrative databases, and very roughly seem to capture what it is that we mean by the denominator here, which are what are these efforts that are trying to bring a technology to market, and are they becoming more or less successful over time? The problem is when you go to look at data, it's actually not clear at all what is or isn't a clinical trial. Like this is everybody I've talked to about this has been surprised, counting the number of clinical trials that are running at any point in time, and at each point over the past, say, 20 years. It's actually really challenging. If you open PubMed, I came up with 5 different ways that I might count the number of clinical trials that exist. The National Library of Medicine calls this green line at the bottom clinical trials. This teal line, these are publications that include some reference to a clinicaltrials.gov registry number. This purple blue line, these are publications for which there's some keyword that made me think maybe it was a clinical trial. The green line, the National Library of Medicine uses a word that seems like a clinical trial. And then this purple line is everything contained within all of these sets. And the main thing to kind of keep in mind here is that I can construct a series in a lot of different ways using this off-the-shelf data that suggests, maybe we're spending lots and lots on clinical trials over time, and this quantity is really sharply increasing. Maybe it's more or less flat, maybe it's decreasing. But that data quality here can have a really substantial impact on what we think the correct answer about research productivity in this market actually is. Just as an aside, nominally, the federal government is keeping track of the number of clinical trials being run. The FDA does know the correct answer to this number, and they aren't sharing this information with researchers at the moment. Clinicaltrials.gov came into effect in the year 2000, and compliance has increased kind of in fits and spurts over the last 25 years, but isn't necessarily a great census for what it is we're trying to measure here. So in this paper, I'm not going to spend very much time on the methods that we use for this. I'm really happy to talk about this offline or in Q&A. We basically introduce a new procedure for identifying clinical trials and publication data. And the idea is measuring research with this kind of level of granularity requires a precision that humans are really good at. If you give me a bunch of publications, I can tell you what is a clinical trial and what isn't. Standard machine learning performs really poorly. For any of you who ever used Cochrane tools to write a systematic review or a meta-analysis, these tools do a really good job of identifying true positives and also a really good job of identifying false positives. And so we introduce a method that allows us to do better than this and construct what we think of as a consistent series for this measure of the quantity of research effort in this kind of narrow part of the medical research ecosystem. And we find that when measured consistently, the number of clinical trials and publication data. So if you keep in mind this increasing trend I'm showing you here, we find that when we revise the measures and we take into account the fact that some of these objects are hard to pin down, the line is essentially flat. And so what I'm showing you on the x-axis is each year of data in PubMed. And on the y-axis, I'm showing you the growth in the number of things that I would call a clinical trial in my data relative to the starting year of 2010. We see a little increase in the middle of the 2010s, but we're hovering around 0 to 5% growth in the quantity of clinical trials, which looks to me like essentially a stable series. At the same time, what's been going on, if this plot looks like this, there's these sharp increases that are coming from somewhere, and they're not coming from clinical trials. They're not coming from the thing that we think is really productive in this setting. The quantity of other medical research, the quantity of meta-analyses, the quantity of things that look a little bit like clinical trials, but are more focused on diffusion or are more focused on summarizing the findings of increasing research, measured in lots of different ways, these are increasing. So while clinical trials totally stable over this time period, we observe on the order of 60% growth with our most liberal version of this measure in other medical research. And I'm going to give you a little bit of context on what falls into these two sets to give you a sense that this is kind of what I intended to be measuring. A natural question is, you see a flat line like this, I'm just counting things. It could be the case that the clinical trials that were produced at the beginning of the decade were much, much more important. These are the big trials of new cancer drugs in 2010. And by 2019, we're running these incremental studies that have a tiny number of patients because maybe it's too expensive or something else in the ecosystem has changed. We construct a couple of other measures that suggest that what's in these trials, at least on observable proxies, is also stable. And so the main thing to take away from this plot and the next one is that if your eyes move from the left to the right side of the screen, everything is flat. And so I'm showing you what share of these trials are publicly funded, what share are cited by one of the top 84 impact factor journals in medicine, conditional on being publicly funded, what is the share that are ever cited by one of these top journals. And on all of these metrics, we see that within this set of trials, we think that things are flat. We see the same thing when we look at citations. Essentially, what I'm showing you here is in each year, at the 0th percentile of the citation distribution, how many cites are trials getting? And at the 99th percentile, how many are they getting? And again, the key thing is the trends more or less look the same if you move from the left to the right side of the screen. An interesting fact that is not as central to the question of research productivity, but kind of interesting to note, is that we are finding consistently across cuts of our data that about 55% of clinical trials are never cited within 3, 5, 7, or 10 years by a single other scientific publication. That's this gray bar. We can also look at various measures of this quantity of other medical research and try to get a sense of what's going on. So stepping back for a second, what Nick was suggesting to you with the Nature paper and kind of what's at the center of the way that we're measuring scientific research is that we often see these sharp increases in the quantity of publications, and we see big increases in the number of patents. And the main question from a research productivity perspective is, does a patent today contain the same amount of science as a patent 20 years ago? Does a paper today represent the same, on average, scientific contribution that it did 20 years ago? And if those units are stable, then it's easy for us to think about productivity kind of increasing or decreasing over time. We look at this set of other medical research, the set of things that it looks like are driving the increase in PubMed. We see on a variety of ways of measuring this, the increase in the quantity of other medical research is due in part to meta-analyses and literature reviews that are very much focused on the diffusion of information. So from the perspective of clinical care, from the perspective of patient well-being, these are interesting objects, and these contain really important information. But within the productivity, research productivity exercise that we had started with, maybe they're a little bit less relevant, and they're driving a lot of the increase in what we're observing. The other fact that's kind of interesting to us is that we see that the geography of clinical trials is more or less stable. So on the left-hand side, I'm showing you across countries that produce clinical trials, what the breakdown is across countries. And I'm comparing that to this set of other medical research. The main observation to make is that the geographic distribution of clinical trials is more or less stable across this period as well, whereas we see big changes in where these other papers that appear to be generating some of the increase in the size of PubMed are coming from. And so this line here corresponds to publications from China. This is a 225% increase over this time period. Every other country in the world put together, with the exception of the US, Germany, and Japan, experiences the same increase. In terms of both the total quantity of increase and the percent change, China is the clear standout in explaining kind of what's happening that's making PubMed grow over this time. The other thing that's happening in the background is that the quality of these papers, at the same point that the number is increasing, some proxies for quality are decreasing. So we saw a lot of stability in the citations and kind of measures of quality for clinical trials. We don't see the same thing for these other publications, as measured by citations, as measured by proxies for author quality. This set of other papers appears to be becoming lower quality, even as the quantity is rising. So this particular paper focuses on the two stylized facts that really support the conclusion that research productivity in medicine is falling, that inputs are rising while outputs are constant. We show that with revised measures, at least in the most recent period, which is what seems relevant from a policy perspective, inputs are also, at least since 2010, constant. And so on this kind of very simple measure, we don't find support for falling research productivity in this industry. It's worth noting that what I'm showing you is evidence of essentially complete stability. And whether complete stability in a setting where we think we're pouring maybe more resources into the NIH, or there's more research effort going into translational medicine, that might not strike you as a good thing. When I've talked to people at the NIH about this, the fact that the number of clinical trials is stable year on year, It's good news if you think that medical research is in a state of decline and maybe science is stagnating. It's not great news if you thought maybe we were doing something to make this system more efficient and you expected to see productivity be increasing. There's a couple of reasons that you might think that there's constraints in these markets, things like clinical trials. Maybe we don't have enough patients, we don't have enough sites, we don't have enough infrastructure. And those are the types of policy questions that seem very relevant to think about if you want more things from upstream in the medical research pipeline to actually be making it to patients. This is a very small first step toward, can we think about how we quantify medical research productivity? A lot of my ongoing work is kind of thinking about whether clinical trials are efficient, whether upstream scientific research is efficient, how firms make investments. But we kind of think of this as a first step towards saying, what's kind of the state of the literature? Can we improve on it with some better measurement? So I'll stop there and then.
Wow, thank you. Thank you both very much. That was both spectacular and incredibly provocative. A big part of our job here at the School of Medicine is research. And this overall question of we hold our faculty to account for research and research productivity, for publications, for running clinical trials, for discovery. So this issue about how do we hold ourselves to account? How do we measure ourselves? How do we help you understand there are barriers that we should think about? I think this work really opens all of that up. I have a couple of questions, and then Eberle and I have been chatting. Eberle's going to help you get a ton of questions in the Q&A. So first off, Maya, so you need an innovation to even do your work. You need a ChatGPT to figure out what the clinical trials were. Is innovation continuous? As Nicholas, you kind of look at innovation as continuous, but we think about these really important pivotal inventions, CRISPR, the genome, AI, and so is maybe a different way of thinking about this are these big breakthrough innovations continue to occur or continue to occur at the same frequency? The light bulb changed things dramatically. Maybe AI will change things dramatically. Maybe we just get one of these a century.
Maya, you want to take that for medicine?
Yeah, I have one thought about this, which is, so the Nature paper is finding something actually for medicine and across sectors that's quite similar to what we're finding, which isn't, nobody is quite focused on the, have we invented the light bulb? Have we discovered the big transformative discovery in a particular market? But what we can say is it does look like the set of things that are really important, like the right tail of these distributions of discoveries and inventions, is actually stable over time. And so we are continuing to get the really, really big, important discoveries that are coming out of large collaborative research teams. But average measures are falling over time, which is kind of consistent with the idea that you might think if you have, I always think of this as very similar to the way that people talk about occupational licensing, especially in medicine. If you have 100 doctors and then you decide suddenly you're going to have 10,000 of them, you still have 100 people who are probably really, really good at what they had been doing, but the average quality of every unit that you end up adding might decline over time. So there's some concern that you're moving down a quality curve as volume increases of scientific research, but a consistent fact in all of these papers has been the set of things that you might classify as a breakthrough or kind of on the right side of these distributions, that appears to be stable over time.
That's really kind of interesting. One is it's justification for maybe a place like Stanford, where maybe we have extra people on the right side of the, on the tail of the distribution. The other thing, there's an organization called Howard Hughes Institute that kind of picks, we think these are the key scientists and we're just going to fund them. And, so it'd be interesting to look at those strategies. I want to just take one more question, then turn it over to Eberle, because we've got a lot going. One of the measures you think of as productivity, I put money into research, cancer drugs, and then I measure output in terms of life expectancy. And between kind of innovations and life expectancy is an enormous gap. So we have issues about reimbursement, we have issues about access, the structure of the healthcare system, that maybe mutes some of the effects of the innovation, or maybe distorts some of those effects. But the American public really measures not how many drugs we discover, but am I getting better? Am I living longer? So how do is the problem on the science side, or is it on the policy side? Like, I'm not doing a good job translating, these technologies to patients in a way that proves their health outcomes.
I mean, life expectancy is, yes, we care about it a lot. I mean, the UK has this QALYs thing, quality adjusted life years, which is also relevant. So yes, you care about life expectancy, but you also care about the quality of it. The issue is this, as you say, Kevin, this thing is impacted by so much else. In fact, there's the famous Case and Deaton paper in the PNAS showing that American life expectancy actually started declining. It was nothing to do with, reversing medical progress. It was due to deaths of despair. It's like drug, alcohol, suicide. So, and in the UK, actually, I believe maybe has longer life expectancy than the US, mainly because the way their healthcare spending is lower, but it's more equitably spread. So yeah, I mean, that's a very hard measure. It's just so distant, and there's so many other things going on that it's not something we generally rely on.
Errol, let me turn it over to you.
Thanks so much. And yeah, we have a lot of questions. We absolutely won't get to probably all of them. So please, everybody, upvote the ones you want us to get to first. I'll start with this one. So I'm going with the ones most upvoted. Dr. Lowe asks, only about 30 to 40% of publications in life sciences can be validated and repeated. Is it possible the value has been decreasing over time? Is this a factor?
So my hypothesis would be yes. There are some interesting recent papers that are suggesting that the quantity of papers that can't necessarily be reproduced or aren't based on well-collected data is increasing over time. So there's some evidence that the power of observational studies kind of on average are declining over time in life sciences. A lot of journal editors have thought in the past couple of years about whether this reflects very strong incentives for people to produce quantity over quality. So if you were concerned about the reproducibility of publications, you might be more concerned about it as these academic incentives are shifting. The other thing, which I know people in the US Patent Office are thinking about, and I suspect people who are journal editors are thinking about, is that with things like ChatGPT, the cost of producing a publication is declining. And so you might be concerned that all of these kind of incentives that prioritize quantity over quality people are encouraged to produce even more papers that aren't necessarily reproducible or aren't based on well-designed studies.
Excellent. I have a question here that's got a lot of upvotes from Dr. Nichols, our Chief of Pulmonary Critical Care Division. He says there's a huge shift in business funding R&D since 2010 National Science Foundation report. Government funding relatively much lower. Getting to the quote unquote starting line for your first R01 in your 40s, it's harder and harder to even get started for many, the draw of business focusing on the bottom line. Does your research support the idea that the difficulty of individual NIH-funded researcher getting started and business being so key in research could account for less fundamental discovery?
Yeah, so I'll start first on that's, maybe I was going to go from the Fantastic Four to the Fantastic Five. I might have added that in. So just to give you a fact, it's totally spot on. So if you look in the US, if you go back to the 80s, 2/3 of R&D was, or 70s actually, 2/3 of R&D was government funded, 1/3 was business. It's now flipped. And a lot of people think that government funds R and business funds D. So government's much more basic research that maybe doesn't immediately, turn into products or, drugs, etc. But in the long run, it's much more important. and business tends to fund end of the line stuff, more development. So that has been another big concern. In fact, Stanford University itself was built up. If you look at the history of Stanford pre-World War II, it wasn't really very research focused, and then post World War II there's a big increase in government research grants, a lot of it around defense that Stanford got, and it really took off. So I'm totally in agreement. Economists in general think there's more what I call knowledge spillovers from basic research, the R bit, which tends to be government funded, and that's the more important long run part of it. And that will trickle down into, because there's less money in government funding, it is harder for individual scientists to get grants and later in life, and many of them will not be missed. I totally agree. And it's really we all know that the government's in massive deficit and it's pretty scary, but as economists, one of the things you really don't want them doing is cutting back on government research funding.
A question here from Dr. Ash, also on health policy. He says, great presentation. A big part of research productivity is whether effective innovations are adopted. About 50% of good ideas spread. This process itself is subject to research. The study of how or why things get adopted, often called implementation science, would seem to be a good target for increasing research productivity. Could you add to your estimates?
I'm happy to have a go. Or Maya, do you want to, whichever you want?
Either is good. I will say I worked on an implementation science team for many years focused on HIV. And so this is a topic that's very close to my heart and very close to my research. And one of the things that I found kind of peculiar when I started working in this space is that the way, kind of dating to Zvi Grillickies, who is a kind of giant in measuring these objects for economists in the 1980s and 1990s, people often distinguish between two measures. One is how good are we at just getting the idea? Like how good are we at producing the technology? And how good are we at diffusing the technology? And so there's a distinction between invention and diffusion. So we've mostly been focused on just, are we getting the ideas? Are we good at getting things essentially from labs through the FDA or onto the market? But right now we haven't done anything that looks very closely at diffusion. There's a few papers that manage to do this, but I think I haven't seen anything that builds it into these kind of productivity measures. Nick might know this better than I do.
Well, I was going to come up with a very kind of Quentin Tarantino comment, everything connecting in itself. The reason I know Kevin is Kevin and I first met, 15 years ago. Maybe, I don't know, Kevin, not long after you come to Stanford to talk about the adoption of management practices, particularly in healthcare. So there's this huge literature. In fact, many years ago, I mean, going back 20, 25 years, I worked in McKinsey in London, in the London office, and their biggest customer was the NHS. And they're trying to put in place some kind of relatively standard management practices from retail and manufacturing into healthcare. None of it's very, exotic or exciting around data use and incentives, etc. But it was hard work. And that's, if you think of innovations, people often talk about products, but another huge innovation is process. Just organizations are much better managed, they're more data rich, they're more focused on incentives than they were 50, certainly 100 years ago. But that is an area where if you look across organizations, you can see enormous variations. So yes, I think adoption is just as important. Generally, it responds to market, less in kind of, to some extent, it responds to market incentives. So competition information. But yeah, that's another big field. I've seen less evidence on whether that's changed over time, actually. There's an S curve of adoption. If that's been stable, the key thing is the new ideas coming out. But you're right that S curve can be 10, 20 years, actually. Like those studies on beta blockers, for example, the adoption of those, there's like 20, 30-year gaps across. There's the Dartmouth has that health atlas, and you see it across countries as well.
Dr. Rogers asked a question. Any early thoughts on COVID research and impact? There were a ton of clinical trials in a short amount of time. A lot of your scales end in 2020, so maybe it's too early to say.
Yeah, so they intentionally end in 2020. We stop our data in February of 2020 because what you see is this really, really sharp increase in the quantity of things that look like clinical trials at the time and a really sharp decrease in the share of those, so that the share of those clinical trials that have ever been cited is much, much higher. There was an interesting paper that came out, I think Andrew Gelman is on it, but I can look for it and put it in the chat, that goes through basically how well designed the COVID studies were. And basically there's some indication that they ended up being, the vast majority of them were quite small and not necessarily powered to detect the effects that they were trying to detect in those studies. The best ones actually came out of the NHS in the UK. But we figured kind of disentangling what stable trends in research productivity are from this kind of one-time big reallocation of effort toward COVID and the cessation of all of the other studies at that time was it was less informative on the question of the design of policy. But that's, yeah, exactly the right kind of thing to be thinking about at the end of that time series.
But Errol, before I forget, one comment for everything is Maya and I are also very happy to share our slides.
Yes.
You know, we're both in Stanford. There's no intellectual property on them. So if anyone else wants to use them, I'll post, we can both post them. And also if anyone, feel free to contact us directly.
We'll send a follow-up recording of this email to people who can join. So if it's okay with you, we'll attach the slides as well.
Totally, yeah.
I was texting Kevin during this presentation. He often has some of the most important topics. This is a great example. I apologize. We have so many questions we can't get to. It's always a reflection on how important the work you both are doing that engages our audience so much. So thank you so much for being here today. Kevin, thank you for setting this up, and thank you both for presenting in your time today and sharing all the work that you're doing.
Oh, it's lovely to so many friends and colleagues, and I'm sure I hear about this when I bump into people for the next month at my kids' school pick up and drop off and various university committees.
Yeah, thanks for having us. This is fun.
Thanks again. Thanks everyone for sticking around. Have a great rest of the day.
Bye.
Bye.
The preceding program is copyrighted by the Board of Trustees of the Leland Stanford Junior University. Please visit us at med.stanford.edu.